I'd like to introduce you to a benchmarking methodology we developed in the core extra project and some new tools to make it nice. So the main idea is to maintain a directory of benchmarks similarly to how you would keep a directory of tests in your project. And each benchmark is sort of documents an optimization experiment that you performed. The main advantage of this is that it keeps the benchmarks reproducible. Since browser targets constantly evolve, tricks that you might have used to micro-optimize some code earlier that produced wonderful results might become obsolete and in fact might decrease performance. So having the ability to periodically re-benchmark is very helpful. But the benefits don't end there. It also acts as a learning resource for your team. It's a record of what was tried and what worked and what didn't. And this can help everyone not repeat work by trying to optimize things that have already been tried and perhaps failed. But also sometimes benchmarks have methodological flaws in them that make the conclusions you've reached invalid. Having the record of that in your code base where somebody can notice that problem, fix it, and come up to new conclusions about the performance characteristics of your code is very useful. So let's find out how our new elm-bench tool helps to optimize some code. Okay, so I've got here a little demo file. It's a little collection module that provides some sort of list extra like functionality like deduplicate, frequencies, and some others. And we would like to figure out how to optimize some of these. You might notice that this code has some maybe less than optimal performance characteristics. So let's see if we can measure that and figure out a more powerful version. So I'm going to jump into my terminal here, and I'm going to run elm-bench init. And this has created a benchmarks directory for me with an elm.json here that installs elm-bench for us, and a little sort of demo-ish entry point here for us. So we would like to go and optimize this deduplicate function here. So for this, I'm going to run elm-bench optimize. And then I'm going to say collections.deduplicate, and I'm going to give it an arg here. And so the arg is what argument I should run this one with. So I'm going to say list. We're going to make two lists that contain duplicates but not right next to each other. And let's run that. And if we go into we've now got collection/deduplicate baseline and made us a helpful little copy here of that file. Optimized is identical at the moment. So these are the modules. Baseline is we're going to keep identical. Optimize is where we're going to put our new optimization ideas. And we'll see that this has created a nice little thing. So we can now just delete this suite here. So we can now type in elm-bench run to run our benchmarks. And as expected, we see that they're virtually identical in their performance. They're both getting about 1,000 runs per second here. So let's try to optimize here. So I'm gonna paste in here a slightly more elaborate definition here. So this one uses set membership to track which items it's seen, and then only appends items that it hasn't seen yet, and runs that in a fold. then throws away the set when it's done. Okay, so let's run this again. Just make this a little bigger. So I'm going to rerun this benchmark. And here you see verifying benchmark correctness. Benchmark verification failed. Some implementations produce different results. And underneath we see basically pretty typical Elm test output. And it seems like we ran a test here, and we see right away that our deduplication functions actually, they look like they work, but they produce results in a different order. So our new optimized function is not doing what we're expecting it to do. It's changing the order of the input, which is not acceptable. So yeah, it might be faster, but it's also broken, and we don't want to spend our time trying to optimize a function that doesn't actually do what we want. So in this case, it's a typical bug. We put foldle instead of folder, so we can fix that. Rerun our benchmark, and this time we see our test has passed, and we're ready to start the actual benchmark. And sure enough, we've got the results here, and our optimized version is so nearly 8 times faster. So this is a good optimization. Okay, now let's look at another feature, which is scaling analysis. One of the ways benchmarks can fail is that we have to choose this argument here. Sometimes that can make a big difference, because sometimes some algorithms behave better under certain circumstances while others behave under different circumstances. So let's see if we can do something where we can analyze that. Adjust this to put in our thing, and I just want to show you here what we're testing. So we have here 2 functions that do list sort of find elements common to both lists, so almost like a set intersection, but for lists. And here we have sort of a naive version, and here we have one using sets. Okay, so we want to make sure, see how these perform. But here we've set this up as using bench.scale, which is for understanding the scaling properties of our algorithms. And you can see here that we're going to benchmark this at a bunch of different sizes. So we're going to look at, pretty small inputs, some medium-sized inputs, and some reasonably large inputs. And we're going to use the input size here in this function to help us generate input of that appropriate size. So list range in this case does a good job of that, and we're gonna use that, and we have those 2 versions here. Okay, let's run it with elm-bench run. Okay, this is completed. Let's open that a little bigger. And we see right away that we get right in our terminal a nice little graphical thing. This one's a little chunky. If you're using a terminal with iTerm to image support, you're going to get a nicer image. This is kind of a fallback Sixel-based output. But nonetheless, we can see quite clearly what's going on here. So the interesting thing is these performance, no, these are log scale, so the differences are actually not small. If we had only run this benchmark with a very small input size, so maybe a list of only 5, we would see that the naive version actually outperforms the set-based version by a decent margin. But of course, if we had only tried running with a fairly large input list, we would see that the set-based version smokes this version by a good margin. And of course, in this case, there's an algorithmic difference. So if we extended this much further on, into the tens and hundreds of thousands, we would see this difference keep widening. But interestingly enough, I think this full picture gives us a good idea that if we're expecting this function to be used with lists, something like, I don't know, 60 items or less, actually the naive version will outperform the set-based version by a decent chunk. So if this is mostly being used on very short lists, which, to be fair, in UI applications is not infrequently the case, then actually having a naive version would have been better. And this benchmarking strategy with this visualization helps us understand this behavior. And that's elm-bench. So we're in it to get started, optimize, to create a little, to do the setup, automate the setup, and then run to actually run the benchmarks. There's a few features I haven't touched on. You can run watch mode to just rerun benchmarks as you're editing. There's a filter to only, if you have a lot of benchmarks, to only focus on what you're running. There's target, which allows you to run use this terminal runner to run in multiple browsers at the same time, as well as Node, and compare those. It's very cool. And other things like fuzzers and so on. But I'm not going to go into all the details. Feel free to look at the README. And I hope you find this tool useful.